Hi there. In this video we're going to talk about the Cayley-Klein model of hyperbolic space. So we'll discuss two ways to define a geometry, then introduce the Cayley-Klein distance function, parallels in the Cayley-Klein model, and talk about the notions of perpendiculars and reflections. Let's get started. So we've got sort of two ways of approaching defining a geometry. We defined the Poincare disk model as a set and a group of transformations. So our group of transformations was generated by reflections in circles orthogonal to the boundary or diameters. So here we had our circle, and then we defined the set M to be given by reflections either in circles orthogonal to the boundary or diameters of the circle. So given one of these objects, we could invert in it, and that would switch the two halves of the region, and we would wind up with an element of our group M. So M here being the set of transformations corresponding to reflections in circles orthogonal to the boundary or diameters. So here we started with the symmetry group, and this eventually, after some time, gives rise to a notion of length, or a metric. We can also go the other way. We can start from a notion of a distance, and then define the group of transformations that preserve that distance. So the isometry group of a distance is going to be all of those functions f, which preserve the distance, so that the distance after applying the map is equal to the distance before applying the map. We require that these functions be continuous bijections so that they have inverses, so that we wind up with a group. So thus, the notion of length is defined first, and this gives rise to a group. Okay, let's see how this works in the Cayley-Klein model. We define a notion of distance on the hyperbolic plane in the following way. So given a pair of points AB, we can now form a Euclidean straight line through A and B, and that will intersect the absolute at a pair of points xy. The distance from A to B is then defined to be the logarithm of this ratio. So we take the distance AX, the distance bx, the distance ay, and the distance by. And this forms the components of the logarithm that we use to measure distance. So the Cayley-Klein model is defined to be the disk together with the isometry group of this distance. The parallels in the Cayley-Klein model behave very similar to what we saw in the hyperbolic disk. Given a pair of points AB, we can form a line joining them, and all of the lines through this point P do not intersect the line through AB. So what we obtain is that given a pair of points AB and a point P not on that line, there are infinitely many straight lines through P that do not intersect AB. So lines through PX and PY are parallels to AB through P. So we call this line and this line parallels to AB. And any other line through this we call a non-intersecting line. Okay, so once again, this is very different than the notion of parallels in the Euclidean plane, which says that there's something rich and special going on in the hyperbolic plane. Again, this is evidence that the hyperbolic plane does not satisfy Euclid's fifth postulate. Now let's move on to the notion of perpendiculars. A reflection with respect to L is going to be defined to be a non-trivial isometry, so an element of the isometry group, such that f of p is equal to p for each point on L. So if we have a line here, L, this map is going to switch the components on either side of it, but it's going to send every point on the line to itself. So this defines a reflection about the line L, and we say that L1 is perpendicular to L2 if the reflection in L1, or the reflection in L2 maps L1 to itself. So if we call this L2, then what we're going to get is that these two lines are perpendicular if the reflection in L2 maps L1 to itself. Now notice these points here will move to the other side of the line. So they're not fixed point-wise, but L1 as a set is fixed by the isometry F. This gives a definition of right angle, but the angles in the Cayley-Klein model do not agree with the angles measured on the diagram. So I encourage you to check this out in the book. We're going to discuss this in more detail in class. Thank you for watching.